Hi everybody! Today I wanted to make a video again about interference figure projections. In one of our previous videos I showed off the in-person large-scale demonstration I do for this using a custom-built polariscope. However, that large-scale polariscope and large-scale mineral slices are kind of expensive, and we've got a much better, cheaper, smaller option that I actually have for sale as well at the eBay store Snellius Minerals. These devices are set up to project a single interference figure for a specific mineral, and let me show you how they work. In our previous video on interference figure projection, we talked about how our custom-built polariscope designed to project interference figures works. We've got a light source which consists of a flashlight with a converging lens on the end. The light from our flashlight then travels through a light diffuser, which in this case is just a simple piece of white tracing paper. The light then travels through our lower linear polarizer and emerges as plain polarized light. This plain polarized light then interacts with our mineral sample in the sample area, and then travels through our upper linear polarizer, whose vibrational direction is perpendicular to the lower linear polarizer. We are currently looking at a side view of our custom polariscope. Here's actually a side view of the small interference figure projectors, and although they are tiny, they effectively have all the same components as our much larger custom-built polariscope, and all we need to do here is add a light source in order to get them to project an interference figure. There are two different styles of this device. This first group here actually omits that light diffuser that I mentioned, and the second group has it included. In omitting the light diffuser, the first group of devices can also act in a manner similar to an ORS, an optical ring sight. The development of the optical ring sight is detailed in the book Rings of Fire, and I suggest picking up a copy if you want to learn more about the history of this ingenious device. Here's a figure detailing the various styles of optical ring sights, and the first small interference projector that we take a look at is very similar to this style of ORS, the main difference being that our mineral specimen is going to be muscovite mica instead of calcite. These interference figure projectors lack that light diffuser, which allows us to look through them like so. And so what you'll see here is actually the interference figure for our muscovite mica, which is biaxial. This is an acute bisectrix or BXA interference figure that occurs perpendicular to the cleavage plane of our muscovite mica. A more in-depth look at muscovite mica can be found in the video Snellius Minerals LLC Oriented Muscovite Mica Sheet. We're not really seeing the full effect here, and so I have to tilt the device a little bit in different directions in order to give you a better sense of the full interference figure that we could see. The downside with the small interference figure projectors is that we can't rotate the sample or the linear polarizers. However, what we can do is make a whole bunch of these, all with different angular relationships between our minerals and our linear polarizers in order to get different effects. For this next projector, the muscovite mica is in the same orientation. However, I've lined up my linear polarizers such that their vibrational directions are parallel to one another. This is similar to this style ORS device, except once again, we've replaced calcite with muscovite. Taking a look through this projector, we see a similar interference pattern. However, the isogyres in this interference pattern are clear instead of black, and you can see that as I tilt the device a bit. Our next projector is going to show the interference pattern for muscovite mica for when we've rotated our muscovite to extinction at 0 degrees, and also have our polarizers crossed. Almost all the light is blocked out by our isogyres until we tilt the device a little bit to look more down the optic axes. Let's switch now from looking at biaxial muscovite mica to the uniaxial mineral quartz, although quartz also has a special power for us today. When looking down the optic axis of quartz with crossed linear polarizers, we're going to be able to see some of a uniaxial optic axis interference figure. The colorful circle at the center of this interference figure is actually caused by optical activity. Once again, we can tilt our projector a bit to show you a little more of the overall interference figure as well. If you'd like to learn more, please check out the educational video, Snellius Minerals LLC Quartz Slice. Now we'll transition to another uniaxial mineral with crossed polarizers, and that will be a slice of beryl. Our beryl crystal isn't quite as clean and nice as some of the other minerals we've been looking at today, and so the interference pattern is a little bit off. However, overall it is a uniaxial optic axis interference pattern. Once again, you can see more of it as we tilt the device in a couple different directions. We can use these techniques as well to generate some more complicated interference patterns and show off concepts like how accessory plates work in a petrographic microscope. This projector consists of two pieces of muscovite mica at 45 and 135 degrees to extinction. The pieces of muscovite are about the same thickness, and our polarizers are crossed in this orientation. This is effectively showing a destructive interference between the interference figures of our two muscovite plates. And also, I just think that's beautiful and kind of amazing how well that works. Our next projector is the same as the last. Instead of having crossed polarizers though, we have our vibrational direction of our polarizers parallel to one another. Once again, a pretty trippy and cool looking figure. The last of the projectors that we'll look at without a light diffuser is a piece of phlogopite mica. This phlogopite mica is uniaxial, and we can see the central part of a uniaxial optic axis interference figure here. We can also see a bit more of the interference figure if I tilt the device in a couple different directions. So the advantage of the small interference figure projectors that do not have a light diffuser is that we can use them in a manner similar to an optical ring sight. So let me show you what happens if we try to use our small interference figure projectors that have a light diffuser in the same manner. This projector consists of a piece of muscovite mica at 45 degrees to an extinction with crossed polarizers. If you look through the side with the light diffusing piece of paper, you see a piece of paper. And if we flip it and look in the other direction, you will see an interference figure, but of course we can't see anything through that interference figure because there's a piece of paper there. Here's another example of the small interference figure projectors with a light diffuser. This one is illustrating yet another complicated concept. Here I have a piece of phlogopite and a piece of muscovite constructively and destructively interfering. This is actually how you can determine optic sign. So for our small interference figure projectors with a light diffuser, they aren't as useful to us under normal lighting conditions or being able to look through them. However, they are a bit better at projecting an interference figure. Let's now explore how our small interference figure projectors actually work as interference figure projectors. This is best done in a darkened room, and what we're going to do here is just shine a flashlight through each of our interference figure projectors, and we'll start out with the interference figure projectors that are lacking a light diffuser and see how they work. We've got muscovite mica with crossed polarizers at 45 degrees to extinction. Next up is muscovite mica with parallel polarizers at 45 degrees to extinction. Who can forget muscovite mica at 0 degrees to extinction with crossed polarizers? And you can tell my isogyres are a bit off there, so it's not really at 0 degrees. Sorry about that. Next up, quartz with crossed polarizers and strange optical activity. Then there's the not so perfect beryl crystal looking down the optic axis with crossed polarizers. Next up, two muscovite plates of similar thickness at 45 and 135 degrees with crossed polarizers. Then two muscovite plates similar to our previous example, however with parallel polarizers. And finally, for the small interference figure projectors that lack light diffusers, a piece of uniaxial phlogopite mica with crossed polarizers. Now our next small interference figure projector is going to have a light diffuser, and I want you to notice how this actually improves the projection quality of our interference figure. So we end up with a much broader and more complete interference figure for our muscovite mica. Here you can see the two different styles head to head. The interference figure projection above lacks a light diffuser, and the interference figure projection below has the light diffuser. So that's really the trade-off. Removing the light diffuser allows us to use our interference figure projectors also as an ORS under normal lighting conditions. However, it actually projects an interference figure a little bit worse. And just to show off one more projection, here we have our muscovite and phlogopite with cross polarizers. They're interfering constructively and destructively with one another in such a way as we could determine the optic sign. If you'd like to try any of these experiments out for yourself, you can find the small interference figure projectors for sale at the eBay store Snellius Minerals. There's quite a variety of these that can be made, so I don't have the full complement on Snellius Minerals at any particular time. However, feel free to reach out to me at snelliusminerals@gmail.com if you'd like anything specifically made. Or if you have any other thoughts on fun optical mineralogy videos you might like to see. Here are the references I used in the creation of today's video. And special thanks to Larry Hughes, author of the book Rings of Fire, for allowing me to use his ORS figure. Thank you again for watching, and have a great day.